All right, everybody, welcome back and welcome to Chapter 14, Part 2. I realized after Thursday's class I didn't talk much about dipole moments, polarizability, and the movement of electrons in conductors. So what we're going to do is hopefully cover most of that in this online lecture. So let's get started. All right, so at the end of the day on last Thursday, we had developed the dipole electric field for on the axis and perpendicular to axis to a dipole as these two equations. So what we're going to do is use these to talk about the dipole moment of a dipole field. So we have these two terms Q and S here that show up in both of these. So what we're going to say is that normally when we have this dipole, we have our two charges, our plus charges and our minus charges. And what I'm going to say is this, I'm going to define this thing as P. And yes, I know it's the same symbol as we use as momentum. P vector, this P is the dipole moment, and the magnitude of that vector is always equal to the charge times the separation of the dipole. So which way does P point? What points, it points from the minus charge to the plus charge. So if we plug these substitutions for the dipole moment back into our electric field calculations, we get a change in the electric field for the dipole moment. Well, why do we need to do this? Well, we're going to be talking about dipoles that are created by, are being induced by other charges, and we need a way of representing the dipole moment. So P is a vector. It's a dipole moment vector. It points from the minus charge to the plus charge for a dipole, and it has the magnitude equal to the charge on one of the charges times the separation or distance between the two charges that make up the dipole. So, polarizability. This is a term that is associated with how easy it is to polarize a particular material or separate the minus charges and the plus charges a little bit to make it look like a polarized. So, normally what we have is some point charge out here, this red area, and some neutral atom over here. Now when we put the point charge in, it's going to induce a dipole, right? The minus charges that are in this neutral atom are going to move towards the positive charges, and the plus charges are going to move away. And these two charges are separated by distance. Well, what is inducing the dipole is a force that's created by the electric field of the dipole. That's a force that's created by the electric field of the point charge, not the dipole, of the point charge that induces the dipole. So we'll move that vector out of the way because it's going to cloud up. So right now that we have a dipole, we have a dipole moment, this blue arrow, and that's what we're going to call the induced dipole. So, how do we figure out what the induced dipole moment is? Well, if it's an induced dipole, it has the magnitude of equal to alpha times the applied electric field. And alpha is referred to the polarizability, and it is a constant depending on the object that's being polarized. So all different objects have different polarizabilities. So that's going to be inherent, so we should know what the alpha is or be able to know the dipole moment if we know the induced dipole moment and the electric field that's inducing it. So this applied electric field is external to the dipole. In our case, it's this electric field caused by our point charge, positive point charge over here. Alright, so now that I have this dipole, induced dipole moment, Well, that has an electric field. And that electric field is acting on this point charge, or this point charge over here can see this electric field. I've got to draw it in as yellow. But we need to figure it out. Well, it's on the axis, and I just realized that I think I have the wrong formula for the dipole here. It should be 2p, because it's on the axis and not perpendicular to the axis. I apologize for that. And then, well, how do we figure out what this electric field actually is, or the strength of the electric field of the induced dipole? Well, I got to know its dipole moment. Well, since what is producing the electric field is this induced dipole over here, well, I put in its dipole moment right there. And then, well, what is the applied electric field that's creating it? Well, that's the point charge that's induced this dipole already, the point charge over here of plus q, and so I can put that in there. And now, if we group everything together, we find out that this new induced dipole does not go as 1 over r squared as a point charge does, or 1 over r cubed as a physical dipole does, but it goes as 1 over r to the 5th power. So this electric field is much, much weaker than electric fields from an actual dipole or from the electric field of an actual point charge. Alright, on to conductors. So conductors basically allow the movement of charge very easily, or free charge around. And the way it moves it around is this idea called the drift speed. That is the average velocity in which a charge, in our case we'll be talking about electrons, moves in a material. And the way we can, a model for that drift speed, okay, is the average velocity is equal to u, which is, that's called, u is the, what's called the electron mobility of a material, and E net, that's the net electric field seen by the charge that's being moved. It doesn't have to be electrons, it could be ions. If it's in a fluid and there's ions floating around, it would be the electron mobility of those ions that are floating around. So if it's an electron, we call it the electron mobility, but normally it's considered the mobility of the charge. And U depends on the material in which the charge is moving around in. So there's different values for different conductors. There's different values if it's an ion in a liquid. So by definition, as we talked on Thursday, the electric field in a conductor, if it's in equilibrium, means that the net electric field is 0. So by definition, if the net electric field is 0, then the average drift velocity of any charge in this material also has to be 0. But that has to be in equilibrium inside the conductor. Alright, so let's model this metal. So the model we use is called the Drude model. And basically what we're going to do is we're going to apply an external electric field to the metal. Since it's external, the charges that are in the metal should experience a force. And then again, what happens to the momentum of an object experiencing a force? Its momentum should change, right? So knowing this, we should be able to calculate the velocity of this charge. So let's do that. Alright, so we have our Newton's second law here. The rate of change of momentum should be equal to the net force acting on the object. And since there's an external electric field, we know that the net force should be the charge that's being moved times the net electric field. And in this case, we're modeling a metal, so the charges that should move around are an electron, or should have the size or magnitude of the electron. So if we approximate the derivative as a change and rewrite it, I get the change in momentum is equal to the force times delta t. That should be familiar. And I can write the change as the final momentum minus the initial momentum. And what we're going to assume is that the initial momentum of the electron, just right when the electric field is being applied, should be 0. So this gives us a way of calculating its final momentum. And by definition, alright, so we get our momentum. And again, momentum is equal to the mass of the object times its velocity. And so if we solve that for velocity, we get that the velocity of this electron should be equal to the electron charge times the net electric field times the change in time in which this moment force is acting on, divided by the mass of the electron. So let's look at this metal. And let's say we graph the velocity of this charge versus the time. And what we would see is that our force is constant over a particular time. But then at this time, at some time, the charge inside the metal could hit something. So basically an atom that's in the way, and then this electron with velocity would immediately go to 0. But the electric force is still there, and it's going to start moving, and it'll be another period of time, and it'll hit another object that's in the metal, so an atom or an impurity or something that's in the way of the path of the electron, and it'll start moving again once it's stopped, and it'll hit something else and stop. And this will keep going on and on and on, depending on what's in its way. The amount of time that this electron moves, or its velocity change, can be different. So you might ask, since it's had velocity and go to 0, what's happening to the kinetic energy of the electron during the collision? Well, it has a collision with the atom, and the atom absorbs some of this energy, and we see this absorption of energy as the heat, I should say the temperature of the object should go up. So this is why when you put electricity through things, they tend to warm up. Alright, so what we're going to do is, if you look at this graph of the electron moving through the metal, you see that there's definitely different times that before the electron has a collision. So what we're going to do is try to take the average time the electron moves, and if we do that, that would give us the average velocity. And so we're going to multiply this. So we're going to use this as our model. So we have just used Newton's second law to calculate the average velocity of a charge in a conductor. Well, this model looks pretty close to the model we were talking about earlier, where the average velocity is equal to the electron mobility U, or the mobility of the charge U, times the net electric field. And so if you look at these expressions, both of them have a net electric field, and both of them have an average V. So what's the difference? Well, it's one has U and the other one has the magnitude of the charge times average delta T divided by M. So what we're going to say is our charge mobility is equal to the charge, the magnitude of the charge on the electron, times the average time in between these collisions as it moves down the metal, divided by the mass of our object. And basically we find out that these different these different mobility of charges, constants U, depends on the amount of time that these electrons can experience this force before colliding with something in the metal. So each metal is different.